Okay, so our last but absolutely not least speaker for this track is Elad Levi. Elad is a machine learning engineer in Sightful, a startup that is creating the first AR laptop, and we will hear Dori Peleg later. His work focuses on leveraging multimodal inputs, in particular vision and languages, in order to build a novel AR operating system. Elad received a PhD degree in mathematics from the Hebrew University. His thesis was in the field of a model theoretic with applications to combinatorics problems, which sounds a bit scary. So Elad will talk on democratizing large language models.
Okay, so let's start. So we will discuss in this talk on the democratization process of large language models, LLMs, that happens in the last year, actually, almost a year and a half. So we will first discuss the challenge of building high-quality LLMs. Then I will describe the recent advancement that allowed to build high-quality LLM with only $600. We'll talk about many improvements both with respect to costs and quality. And lastly, we'll talk about how we can get beyond the basic LLM and extend for more capabilities like multimodality. So up until recently, it seems that OpenAI and maybe few other big companies like Google will rule this field of LLM. And I would like to explain the high barrier to train high quality LLM. So the first challenge is to build the foundation model. And the standard architecture is decoder-only transformer. So we saw the transformer that Chen present. So in this way, you're just using the decoder part. And the model is autoregressive, which means that he predicts the next token one by one. Tokens are parts of words. These are the basic units of LLMs. And the training objective is very simple. You take a prefix of a given sentence, and the objective is to complete the next token. And the model gets punished if this token is incorrect. This is done simply with the cross-entropy loss. Now, the key ingredient is the huge amount of data that is used to train the model. And you can see the GPT-3 dataset, which contain about 500 billion tokens. It contains data from Wikipedia, web texts, but mainly huge amount of crawl data from the whole internet. Now, since they train on such a massive data set, they can train a model with huge amount of parameters. GPT-3 largest model contain 175 billion parameters, and it is big jump in the number of parameters comparing to the previous generation models. Now, of course, training such a big model is very costly, about $4 million. And it's not easy to serve such model on regular instances. So there are many challenges. Now, the second barrier, which is even harder to overcome, is the instruction data set. In order to get to ChatGPT level quality, OpenAI collects large amount of high quality data of user requests, what we call an instructions to the model, and various model responses that were ranked by human. Then they fine-tune their model on this data set and got huge jump in the performances. You can see that the 1.3 billion model parameter with the instruction tuning is significantly better than the base model with the 175 billion parameters. Now in ChatGPT you also have the thumbs up, thumbs down button, which also provide valuable human feedback that of course OpenAI are using. Now, OpenAI also invests lots of effort on the data curation process. You can see how many times the word data appears in the GPT-4 contributor lists, and of course, these are not the annotators themselves. So let's talk about the revolution. So the revolution starts about 1 year ago when Meta released a new series of foundation models which they called Llama. And the interesting thing is that the 30 billion size model beats GPT-3 largest model with the 175 billion parameters. Now this is very important since 30 billion model size is something that you can run on a regular instance with very basic GPU. So this is very important. Now the main reason for the improvement is the dataset size, between 1 and 1.5 trillion tokens compared to only 0.5 trillion tokens in the GPT-3 case that we saw earlier. This allowed to train the model more time and boost the model performances. Now there is a paper by Google which is called Chinchilla, in which they perform many experiments and got to some scaling law with multiple variables. And I will not go into the details of the formula, but it's interesting to note that according to this formula, we can expect that we can reduce the model size even further and get comparable quality. But of course, the dataset size should be increased significantly. Okay, so there is a price. Since then, there are many stronger new base models that came out. We have Llama 2, on which they train on 40% more data and of course got better quality. Mistral released also a powerful series of models where the 7 billion version outperformed Llama 2 30 billion on all benchmarks. And the recent addition is Google model Gemma. This model outperformed Mistral 7 billion version on some tasks like coding. And actually almost every day there are new, very powerful models that are coming out. Now, the second challenge we need to overcome is the instruction dataset. And for this we have the Alpaca paper. And the Alpaca paper recipe to overcome this challenge is very simple. What we can do, we can distill the knowledge from OpenAI proprietary models. And the way to do it goes like this. We start with a seed of 175 samples with good instructions and responses for these instructions. These were generated by human labelers. Then they randomly sample example and ask Instruct GPT model, this is a model by OpenAI, it's variation on GPT-3, to generate new instructions and responses for this instruction. In this way, they collect 52,000 examples. Then they fine-tune their model, then they fine-tune Llama 7 billion model on this dataset, and the result is a model with comparable quality to Instruct GPT on various benchmarks. Now, since the model was Llama 7 billion, the training process took only 3 hours on 8 800 GPUs. So the cost is about $500 for querying OpenAI models, plus $100 for the computation resources to train the model, and they got very powerful model with only $600. So next I would like to describe various aspects of improvement on top of this basic recipe of Alpaca. So the first improvement is with respect to the data. While using this Instruct GPT model, we have much stronger model, and in Vicuña they used GPT-3.5. This is the model behind ChatGPT, and they collect 70,000 samples, and they got 90% ChatGPT quality. And there are now works like Orca that distill from GPT-4 and of course get better results. Now I want to focus a little bit about this metric. What does it mean 90% ChatGPT quality? So what they did is they take a fixed set of prompts, they generate responses from all the tested model, and they let GPT-4 provide a score for each answer according to some guidelines. And they sum up this score and get to the final metrics. And you can see here that GPT-4 compare very well between the different responses. Now, the second paper I want to discuss is the Wizard LM work. In this work, they have an evolution process that make the instructions more and more complex. So they start again from the same initial seed, and then they have two options. Either, as before, ask OpenAI model to make a new different instructions and responses for these instructions, or they ask the model to make the same instruction more complex. And you can see here an example. You start with 1 + 1 = 2. This is the question. And either you make a completely different instruction, or you ask the model to make the same instruction harder, either by increasing reasoning, like solving some equation, or add a constraint, like proving that 1 + 1 = 2 under the Goldbach conjecture, or adding some dependency. So using this way, after a few iterations, you get very, very complex instructions. So they collect 70,000 instructions and got a model with almost comparable quality to ChatGPT. And actually, they continue this work and collect much more data, much more complex, and they really close the gap to ChatGPT quality. So another very important aspect is the loss function. So the typical loss function in all these works is the cross-entropy loss on the next token completion, which we described earlier in the beginning. And I would like to convince you that this is actually suboptimal objective. Now, if you look at the following instruction of writing some C++ program, you can see that both start to provide the same correct C++ program. However, the prefix is not the same. Okay, it's natural. So the model is getting punished, although he provides the correct answer. Another issue is that there is no severity consideration. If the model responds with "I don't know" or completely hallucinate, he gets the exact same punishment. And it can be shown that this objective is actually encouraging the model to do hallucinations. Okay, this is important. Now, the last thing is that this method is also, at least theoretically, not considered as temporally compositional, which means that you cannot be better than your ground truth. So if you start with the data that was generated from GPT-3, you will not be better than GPT-3, and we want to be better than it. And there are objectives in which this is not the case. So to resolve this issue, we can use the offline reinforcement learning objective. And the RLHF, the reinforcement learning with human feedback recipe, is going like this. In step 1, we simply generate multiple responses from the base model. Then we let human labelers compare between the different responses and rank them according to their quality. And we train a ranking model with this preference dataset. Then we fine-tune the base model with some offline reinforcement learning objective using this ranking model as the reward function. And you can see the huge jump in performances when training with RLHF comparing to the simple fine-tuning. Now, it's important to note that there are actually today new methods to optimize directly on the preference dataset without training separately the reward model and skip some step. Now, observe that you can replace the human feedback with AI feedback that will compare between the different generations. As we saw, GPT-4 doing this task very well. It's also important to note that you can easily steer the model behavior according to your requirements. We can do it either implicitly by modifying the instructions, the guidelines for the AI feedback, or we can do it explicitly by modifying the reward function. For example, reducing 4 if the answer is completely wrong, or add 0 if the model say, "I don't know." Now, another way to improve efficiency during training is by parameter efficient fine-tuning. And one of these methods that I will present is the prefix tuning. And the idea behind prefix tuning is very simple. What we are doing is to add few tokens before the prompt tokens. And we freeze the whole network, and update only these token embeddings, okay? The tokens have embeddings, and we propagate the gradient only on these token embedding. So it's just for intuition. It's not entirely true from theoretical perspective, since we are learning a continuous embedding and we are not trying to bring this embedding back to the language tokens. But you can think about prefix tuning as learning the textual prefix that best describe your task. So for example, if you train the model to translate table to text, the prefix will describe the task, the input is in some table format, and you should translate it to text. Okay, so it's just for intuition, but this is the process. So in Llama Adapter, they used prefix tuning and reduced the training cost to only few dollars from the $100 that we saw earlier. So it's important for cost effective. So in the last section of the talk, I would like to discuss how the LLM model can be easily extended for new capabilities like multimodality. So we can use the prefix tuning framework in order to add more modalities. This can be done by taking the other modality input, in this example, the image, use some strong pre-trained network to extract the embedding, the representation of this modality, and then using projection, project this embedding to the prefix tokens using a shallow projection. Okay, we're using the prefix tokens. During training, we train only the projection and the prefix tokens. And here we can see an example where you have an image of the car and some pedestrians. What we are doing, we apply the visual encoder on the image, projected to the LLM prefix tokens, and then we add the prompt what the car should do here, and let the model complete this sentence. And you can see that the model answered correctly, and he recognized what's happening in the image. So this is how we can add multimodality on the input side. What we can do with respect to the output. We can use a strong pre-trained text to image, audio, video diffusion models. We have very powerful such models that were already trained. And the typical architecture of such model is to take the text, encode it into some token embeddings, and then apply conditioning with the reverse diffusion model. Now, the exact details of the diffusion models are not that important, since what we can do, we can simply freeze the whole diffusion network and try to align the LLM output with the conditioning textual token embedding. This is done by training the model to extract the modality tokens and then train shallow projection that align these tokens to the diffusion model textual embedding. And you can see how many large models were used in this NextGPT framework. All the different modalities, encoders, the LLM, the diffusion models. However, only 1% of the parameters are trainable. And here you can see the result. You ask questions about the image. The model answers the questions, and you can even generate an audio according to the context. And you can play with this model and see the result. It's an open source model. So to conclude, today there are many techniques to get high quality model very cheaply and efficiently. You can customize this model according to your objective. And we saw the reinforcement learning framework, which is highly effective for this purpose. Lastly, there are highly effective methods to extend the LLM capabilities, for example, by adding different modalities. Now, there is a leaked paper by a researcher from Google which claims that Google and OpenAI have no moat and they will be outcompeted by the open source community. And I hope this tutorial explains a little bit these concerns of the big companies. Thank you very much.